Pluto, a remote and enigmatic celestial entity, was formerly recognized as a distinct and valid planet within our solar system. It was regarded as part of the planetary family until more recent thought-provoking assertions by prominent astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into focus. These distinguished experts have made a shocking statement. Pluto could be on a potential crash course with Neptune. But how could such an event even occur? What might be the consequences of such an immense event? Are we witnessing an extraordinary cosmic oddity? Or is there more to this looming celestial event than what initially appears? Join us as we investigate the possible outcomes of a potential Pluto-Neptune collision. Pluto, once classified as a planet but later redefined as a dwarf planet, continues to intrigue and captivate the curiosity of astronomers and scientists within the vast cosmos. Studies by top space researchers suggest Pluto's orbit lies dangerously close to Neptune's. Notable astrophysicists such as Tyson and Kaku have voiced concerns over the potential hazards of a collision between these two celestial objects, which could present a considerable risk to Earth. But how could such a catastrophic event unfold? Pluto's orbit around the Sun is distinct from any other planets in the solar system. It takes an astonishing 248 years to complete a single orbit. This means that since its discovery in 1930, Pluto has not yet completed even one full orbit around the Sun. However, the intrigue doesn't end there. Pluto's orbit is characterized by a peculiar shape, vastly different from the nearly circular orbits of the major planets. What makes Pluto's path even more unpredictable is its 17 degrees inclination in relation to the ecliptic plane, making its orbit far more erratic compared to other planets. This irregularity introduces additional complexity to Pluto's orbital dynamics. One of the most fascinating aspects of Pluto's orbit is its interaction with Neptune. For approximately 20 years in every orbit, Pluto actually crosses inside Neptune's path around the Sun, defying expectations based on their respective positions within the solar system. This raises an obvious question. Why hasn't Pluto collided with Neptune yet? The answer lies in the gravitational interactions of other planets within the system. The study of Pluto's orbit began right after its discovery. Initially, astronomers were baffled by its erratic trajectory. Unlike other planets whose orbits are closely aligned with the ecliptic plane, Pluto's orbital path stood out due to its steep inclination and irregular shape. The mystery surrounding Pluto's orbital behaviors can be clarified by a concept called the three-body problem in celestial mechanics, which aims to understand the movements and interactions of three objects: Pluto, Neptune, and the Sun. Under their mutual gravitational forces, it is similar to predicting the future positions of these bodies based on their current positions and how they influence one another. For Pluto, this problem indicates that the orbits of Pluto, Neptune, and the Sun interact in a complex way. Key terms like asymmetric libration, scope libration, and VSK wobbling are crucial to solving this puzzle. Astrophysicists theorize that the reason all planets maintain their orbits is due to a phenomenon of libration. In the case of Pluto and Neptune, when Pluto crosses Neptune's orbit, their relative positions are offset by approximately 90 degrees. This separation is crucial in preventing their orbits from overlapping and resulting in a collision. Moreover, libration refers to the vertical oscillation of a celestial body within its orbit. For Pluto, this means that whenever it comes closest to Neptune or another massive planet, it is positioned significantly above the plane of the orbits, further shielding it from possible collisions. Another critical factor in this equation is the VSK wobbling, named after the researchers who first explored how objects move in space. The VSK wobbling refers to how the gravitational forces exerted by Pluto, Neptune, and the Sun influence each other's motion. This intricate dance of gravitational interactions helps maintain Pluto's orbit, even when it follows an unconventional trajectory near the Sun. The VSK wobbling is vital in ensuring Pluto's orbit remains stable for incredibly long periods, despite the apparent randomness of the system. This phenomenon guarantees that despite the seemingly chaotic nature of Pluto's orbit, certain forces and patterns help keep everything in balance. These gravitational forces and phenomena play an indispensable role in keeping Pluto's orbit intact, thus preventing potential collisions with Neptune or any other celestial object. The three-body problem is central to understanding how objects in space interact with each other. It reveals insights into Pluto's motion and helps astronomers understand the gravitational effects on other distant celestial bodies, including stars and planets. Mathematical simulations from the late 1980s demonstrated that despite Pluto's unpredictable orbital features, its trajectory remains stable, with only slight variations from its original conditions. These characteristics of Pluto's orbit have stayed consistent over extended periods, allowing astronomers to refine their understanding. Later computer simulations also provided clarity on how larger planets such as Neptune, Jupiter, and Saturn influence Pluto's orbit. Neptune shares a peculiar relationship with Pluto, with a 2:3 orbital resonance. Every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance stabilizes Pluto's orbit. However, Neptune's gravitational force is not the only influence. Jupiter's immense gravitational pull also plays a significant role in ensuring Pluto's orbit remains stable. Saturn's gravity also contributes to the stability of the outer reaches of the solar system. Studies suggest that Jupiter's immense gravity is sufficient to ensure Pluto's trajectory remains steady for incredibly long periods, potentially even billions of years. Together, Neptune, Jupiter, and Saturn may be working in harmony to keep Pluto's course on track, preventing disruptions to its orbit. These irregularities in the planetary system are crucial in maintaining stability within the solar system. Without these forces, the cosmos could be far more chaotic, with objects like Pluto possibly colliding with other bodies or being ejected from their orbits, resulting in turmoil among other celestial objects. Understanding Pluto's orbit is particularly crucial, especially as there are speculations about a potential collision with Neptune in the far-off future. The complex relationship between Pluto's orbital pattern and Neptune's offers a deeper understanding of how neighboring planetary systems operate and interact. Pluto's case demonstrates how even in seemingly chaotic orbits, equilibrium can be achieved through the intricate interplay of gravitational forces and orbital mechanics. It also emphasizes the importance of continuous observation and analysis to maintain our place in the universe. Studying space often forces us to confront the strange and unpredictable nature of celestial bodies. Pluto's orbit serves as an exemplary case of this unpredictability. The potential for orbital resonance, the critical relationship between Pluto's and Neptune's orbits, is a key feature of this dynamic. The 2:3 orbital resonance ratio between Pluto and Neptune ensures that despite their intersecting paths, they never collide. This resonance is an essential component of the celestial puzzle, preventing any disastrous interactions. The resonance, in which Pluto's orbit follows a 2:3 ratio with Neptune's, is a fundamental principle in celestial mechanics. For every 2 orbits Pluto completes, Neptune completes 3. This gravitational resonance helps stabilize their orbits, ensuring that even though their paths cross, they do not collide. This delicate balance is a prime example of how seemingly chaotic systems in space can self-regulate through subtle gravitational forces. In addition to Neptune's influence, other massive planets like Jupiter, Saturn, and even Uranus play a role in maintaining the equilibrium within the solar system. Jupiter's immense gravitational pull acts as a safeguard for smaller bodies like Pluto, by influencing their orbits and preventing them from straying off course. Some researchers suggest that Jupiter's gravitational force might have even prevented Pluto from being ejected from the solar system altogether. These findings emphasize the importance of understanding the gravitational forces at play within our solar system. While Pluto's orbit remains stable for now, changes could still happen in the future. As astrophysicists like Neil deGrasse Tyson continue exploring the cosmos, they provide a deeper understanding of the delicate balance that governs the movements of celestial bodies. The possibility of a Pluto-Neptune collision, although unlikely, reminds us of the ever-evolving and intricate nature of the universe, illustrating the need for ongoing exploration and study of the forces that shape our solar system. The continued study of Pluto's orbit and its interactions with other celestial bodies is not only essential for understanding our solar system, but also for exploring the wider universe. As scientists like Neil deGrasse Tyson continue to examine space dynamics, they emphasize the evolving nature of celestial mechanics and the challenges of predicting the future movements of planets and other celestial objects. The potential for a Pluto-Neptune collision, though improbable, is a reminder that the universe is filled with uncertainties, and even the most stable systems can undergo significant changes over time. Moreover, Pluto's situation simplifies the complexities of orbital resonance, where the movements of celestial bodies are intricately interconnected. The 2:3 orbital resonance between Pluto and Neptune ensures that despite their intersecting paths, a collision is avoided. This resonance is the direct result of gravitational interactions between the two bodies, establishing a delicate balance that has preserved Pluto's orbit for billions of years. It serves as a perfect example of how gravitational forces in seemingly chaotic systems can produce stable and predictable outcomes over long periods. The importance of this resonance cannot be overstated. It is a fundamental principle in celestial mechanics, demonstrating how even the most irregular and complex orbital patterns can maintain harmony through subtle gravitational influences. This understanding of resonance also extends to the broader dynamics of the solar system, where the interactions between planets, dwarf planets, and other objects are essential in maintaining stability within the system. Jupiter, in particular, plays a pivotal role in the overall stability of the solar system. Its massive gravitational influence acts as a protector for smaller bodies like Pluto, helping prevent them from being ejected or colliding with other objects. Jupiter's gravitational effect reaches far beyond Pluto, affecting the orbits of asteroids, comets, and other small bodies in the outer solar system. This further demonstrates the interconnectedness of various objects in the solar system and how their gravitational forces work together to preserve balance and order. Some researchers even propose that Jupiter's gravitational pull may have played a role in securing Pluto's place in its orbit, preventing it from being expelled from the solar system entirely. This scenario underscores the importance of understanding the role each planet plays in shaping the solar system's overall structure and dynamics. The study of Pluto's orbit and its interactions with other planets also highlights the fluid nature of space. While mathematical models and computer simulations offer valuable insights into the behavior of celestial bodies, they also reveal the inherent uncertainties in predicting long-term movements. Minor changes in initial conditions or slight deviations in gravitational forces can lead to vastly different outcomes over time. This uncertainty serves as a reminder of the complexity and unpredictability of space, underscoring the need for continuous observation and analysis to refine our understanding of the forces that govern the universe. In the larger context of space exploration, Pluto's orbit offers essential lessons about the balance of forces that determine the behavior of celestial bodies. The fact that Pluto's orbit has remained stable for billions of years, despite its erratic characteristics, speaks volumes about the power of gravitational force and the self-regulating nature of orbital mechanics. This case highlights the critical importance of ongoing research, as well as the need to continuously improve our models of how planets and other celestial objects move through space. The ongoing exploration of Pluto's orbit and its relationship with other celestial objects provides invaluable lessons about the intricate balance of forces that dictate how bodies move in space. As the study of space continues to evolve, it is clear that understanding the delicate interplay of gravitational forces and orbital mechanics is crucial, not just for understanding Pluto's trajectory, but also for uncovering the broader dynamics that govern the solar system and the entire universe. By studying systems like Pluto's, scientists gain a deeper understanding of the forces at work in the cosmos, which allows them to better predict the behavior of other objects in space. Despite Pluto's orbit being stable for billions of years, the complexity of its motion and interactions with other celestial bodies continues to provoke interest in the scientific community. This unpredictability in the movement of celestial bodies is a key reminder of how dynamic space truly is. The possibility that Pluto's path could change in the distant future, whether due to external forces or shifts in the gravitational influences of nearby objects, serves as a valuable case study for understanding cosmic stability and instability. Even with the current stable trajectory, Pluto's orbit continues to offer a reminder that our understanding of space must always remain adaptable to new discoveries and changing data. The fact that Pluto has remained in orbit around the Sun without significant alterations or disruptions, despite the seemingly chaotic nature of its orbit, underscores the strength and reliability of celestial mechanics. Even when its path crosses with Neptune's, the gravitational resonance between the two bodies helps prevent any catastrophic event from unfolding. This stability is an ongoing testament to the power of gravitational interactions in keeping celestial bodies on course for such extended periods, despite the apparent unpredictability of their orbits. What is equally fascinating is the role other celestial bodies, particularly Jupiter, play in maintaining Pluto's orbit. Jupiter's immense gravitational field exerts a far-reaching influence that helps stabilize the orbits of smaller bodies like Pluto, and this also extends to other objects in the outer solar system. In fact, some researchers speculate that Jupiter's gravitational forces might even have averted Pluto being ejected from the solar system entirely. This highlights the importance of understanding not only individual objects, but also the broader forces at play within our solar system. The stability of the entire solar system is intricately tied to the interactions between these massive planets, dwarf planets, and other smaller objects. The gravitational resonance between Pluto and Neptune, specifically the 2:3 orbital relationship, is a prime example of how cosmic interactions can result in long-term stability. This resonance ensures that Pluto and Neptune, despite their orbits crossing paths, will never collide. This is because the gravitational forces at play keep both objects at a safe distance, allowing their orbits to stabilize one another. Such resonance is not limited to Pluto and Neptune but occurs throughout the solar system. For instance, similar orbital resonances help maintain stability in other planetary orbits, ensuring that the solar system remains relatively stable over time, further emphasizing the interconnectedness of the solar system. The gravitational effects of not only Neptune and Jupiter, but also Saturn and even Uranus help ensure that Pluto's orbit remains undisturbed. While these gravitational forces are subtle, their collective impact cannot be overstated. Their interactions with Pluto and other celestial bodies work together in ways that maintain the structure of the solar system. Without these stabilizing forces, the solar system could face increased instability, with objects like Pluto potentially being thrown into unpredictable orbits or even ejected from the system entirely.